Hello students, today we are going to see some special techniques for simulating discrete random variables. We will see only one technique, that is called Alias method, for simulating random variables which are discrete with finite support. So let us go to the assumptions of this Alias method. Let x be x follow a probability vector, or you can say it as a probability mass function with p equal to p1, p2, pn. This is the PMF. That essentially means probability of x is equal to I is pi. So we are assuming that the support of the random variable is an endpoint set. This is the assumption of our method. So in this particular case, first of all, why do we need Alias method? Is basically this our method will be computationally efficient whenever you have such a setup. That is why we need Alias method. So what makes this method efficient? So let us state our goal, how we are considering this method to be efficient. So the goal is, given a vector of probabilities, I want to express it in terms of n minus 1 probability vectors. I will repeat, given a vector of probabilities, I want to express it in terms of n minus 1 probability vectors. These n minus 1 probability vectors are so special that they have non-zero probabilities only at most at 2 points, and they are valid PMFs. And I want to write my vector P as equally weighted average of those n minus 1 vectors. That essentially will give me, while simulating, at any point in time, I need not have to worry about all endpoints. Suppose you generate a random number u and you generate a simple number, a number from between 1 to n using this random number u. Then you will worry only about that particular number. In that case, it translates to, let us say we have generated a number k, then we will worry only about the random vector qk, not random vector, probability vector qk. And once I am worried about qk, that qk will have only 2 points. So then you will generate another random variable and choose whether we want to choose this point or that point, as if we are dealing with Bernoulli random variables. And we have seen how to generate Bernoulli random variables efficiently in the previous video. So now the method actually becomes very simple for computer. So the computational efficiency increases once you figure out QKs. But the hard part is to figure out how to define these QKs. That is where we will discuss a theory. I will demonstrate through two examples. One is 3-point distribution, another one is 4-point distribution. And we will generalize this theory to an n-point distribution. And that is how we will come to these QKs that are defined here. So this is the goal. Theoretically, it is intensive, but when you put it on the computer, this method is very easy. It will not take much time to simulate. That is why it is the most powerful method as far as the discrete random variable on lattice points or discrete random variables with finite support are concerned. So this method relies on one lemma. The lemma says, given a probability vector, which is a PMF, there exists at least one j such that pj is less than 1 upon n minus 1. So is this assumption justified? Yes, because suppose there exists no j such that pj is less than 1 upon n minus 1. That means all my j's are greater than 1 upon n minus 1, greater than or equal to. If I sum over all these j's, what I will get? N upon n minus 1, right? So n summation over pj's is greater than n upon n minus 1, As you can see, n upon n minus 1 is greater than 1. Therefore, summation over pj's cannot be greater than 1, and hence this leads to a contradiction. Therefore, there exists a j such that pj is less than 1 upon n minus 1. Now, if pj is less than 1 upon n minus 1, and all other all the probabilities should sum up to 1, there should be somebody to compensate that. So that is, for this j, there should be one of his buddy, that is, let us say I, which is not equal to j, which is such that pi plus pj should be greater than or equal to 1 upon n minus 1. Otherwise, the sum cannot be 1. Therefore, this lemma is proved. So now I have a lemma which says that given any probability vector, there exists some j such that pj is less than 1 upon n minus 1, and for this particular j, there is a buddy or alias of this I, j, that is I, which satisfies the relation pi plus pj is greater than or equal to 1 upon n minus 1. So now what we will do is we will use this lemma to characterize these QKs. So as you can guess, if I want to define something in QKs, what I will do is I will use this probability vector, and I will choose this J as one of the candidates of my first probability vector, which has two non-zero points, and the second candidate vector for that other non-zero point will be this I. So this lemma is typically useful for choosing these QKs. Let us see how. So let us take one example where I have a 3-point distribution. So what is my goal? Now I want to split this 3-point distribution in terms of, let us go back to our goal. Since n is equal to 3, I will split this p as 1 by 2 summation over k is equal to 1 to 2 qk. So half q1 plus q2. This is what my goal is. And each of q1 and q2 should have at most two non-zero entries. And how will I choose these non-zero entries? By using these lemma. For example, I will first figure out what is that j such that pj is less than 1 upon n minus 1. That I will choose as my first point, where I will give the non-zero probability in one of the qi's. And then I will choose the second one such that this pi plus pj is greater than or equal to 1 upon n minus 1. Let us do it in that example. So the example is very neat. It has only 3 points: 7 by 16, which is 0.1, half, which is 0.2, and 1 by 16, which is 0.3. Now, what is n minus 1? N minus 1 here, because n is equal to 3, n minus 1 here will be 2. So 1 upon n minus 1 will be 1 by 2. So are there any points which are less than half? Yes, there are 2 points, 7 by 16 and 1 by 16. I can work with any of these 2 points. Let me fix point 3 as the first point. So choose j is equal to 3. That I have chosen using lemma because P3 is less than half. Right? And now I want to choose another point, that is alias of this 3 or a buddy of this 3, which satisfies that P3 plus P2 should be greater than half. Now there is one point. See, essentially this point, if I choose point 1, it is 7 by 16 plus 1 by 16, 8 by 16. It actually gives me half. So I am not interested in choosing 1 as a point. So what I will choose is, I will choose a point which is slightly of higher value, that is 2. Therefore, I have chosen I is equal to 2 and j is equal to 3. So j is equal to 3 is the first point, and a buddy of j is equal to 3 is I is equal to 2. So now my first distribution, first 2-point distribution, which I will consider, will have non-zero probabilities at points 3 and 2. That essentially means it will have a zero probability at point 1. With this understanding, let us try to figure out what is that third point. So what is that distribution? So in particular, I want the result to be of this form. For given any point k, half times qk1 plus qk2 should give me pk. And q1 and q2 will have at most non-zero entries. We have decided what non-zero entries should be there in q1. For example, we have decided that q1 should have a non-zero entry at point 2 and 3. Now, because point 3 satisfies one condition that p3 is less than 1 upon n minus 1, it is also better that q1 will have entire probability mass corresponding to point 3. This is again an assumption which we are following. So if I assume that, that means if I go here in this expression of pk, if I go in this expression of pk, then what I should have is p3 is equal to half times q13 plus q23, and what I am saying here is the entire probability mass, that is p3, should be segregated only at q13. That means I am forcing my q23 to be equal to 0. If I do that, then the matter is very easy. That is, the entire probability mass q of 3 is in q1. So the corresponding probability mass is 1 by 16. So what I want is 1 by 16 is equal to half times q13. That is what is this expression. Half times q13. So you can evaluate what is q13. That will be equal to 1 by 8. Now q1 have non-zero probability masses only at points 2 and 3. That is already decided. So, and it should be a valid probability mass function. q1 should be a valid probability mass function. So what will be q12? 1 minus q13. That is 7 by 8. So I have decided what should be this probability mass at point 2. Now I want to analyze the corresponding impact of this particular assignment q12 on q22. So what I will do is I will look at p2, that is half. I will look at q21. You will divide it by 2 because finally when you are considering this expression, it will be multiplied by half. So then you will get q22 to be equal to, because you have divided this by half, so it will be multiplied by half, multiplied by 2 here. So q22 is 2 times p2 minus q21. This is here. So 2p2 minus 7 by 8, that will give me 1 by 8. As we have already discussed, the probability mass for q32 should be equal to 0. So that condition is in place here. And at point 2, what should be the probability mass is decided. Now q2 can have only 2 non-zero points. So those 2 non-zero points will be 1 and 2. So then you can choose 1 to be equal to 1 minus q22. That will give me 7 by 8. Therefore, the resultant probability vector that we are looking for, probability vectors, two probability vectors that we are looking for are Q1 equal to 0, 7 by 8, 1 by 8. Q2 equal to 7 by 8, 1 by 8. And P is equal to half times Q1 plus Q2. Okay. This gives me the desired distribution. Now let us try to understand, if I go from the algorithm perspective, what will happen to this particular algorithm. Now all these distributions or all these probability vectors are theoretically calculated. So when I will simulate a number, I will simulate a number between 1 to n minus 1. That is via simulating a random number u in 0, 1. I will take a greatest integer function and I will simulate a number between 1 and 2. Let us say the number comes out to be 1. If the number comes out to be 1, I don't have to worry about where to go. I will simply choose this q1 as a probability vector. Okay. Then I will simulate another random variable and see if that random variable has probability which is less than 7 by 8. Random vector or random number u that has probabilities less than 7 by 8 or not. If it has a probability less than 7 by 8, what I will do is I will assign a number 2. Otherwise, I will assign a number 3. Okay. The algorithm is that simple. So it reduces to simulating only two random numbers once we have done this exercise. Okay. So let us go further and try to analyze certain difficulties when we go to 4-point distribution. The method that we use for 3-point distribution will remain applicable to the next set as well. So remember this method, rewind if you want and see the method and then come to 4-point distribution. So let us try to see what is a 4-point distribution. So a 4-point distribution is a distribution which has non-zero probabilities at 4 points. 1, 2, 3, 4 have probabilities 7 by 16, 1 by 4, 1 by 8, 3 by 16 respectively. Now, according to our algorithm, I want to understand what is Q1. Q1 can have only two non-zero points. So in order to decide that, now my n is equal to 3, n is equal to 4. So n minus 1 is equal to 3. Therefore, I want 1 upon n minus 1 to be equal to 1 by 3. That is very clear. So I want to find some pj such that pj is less than 1 by 3. Can you figure out any? Again, j is equal to 3 will be my chosen pj. That is j is equal to 3 means p3 is less than 1 by 3. Corresponding to this, I want something that is greater than 1 by 3. So let us take 7 by 16 plus, so p3 plus p1 is greater than 1 by 3. So I have chosen the points 1 and 3 to be buddies of each other. Now 1 and 3 are buddies of each other. So I will do my iterative calculations as I have shown in 3-point distribution on this. So I want the entire, because P3 is chosen to be a point such that P3 is less than 1 by 3, I want the entire probability mass to be associated with Q31 or Q13. So that forces the first condition, 1 by 8 is equal to P3 is equal to 1 by 3 times Q13. So that gives me Q13 to be equal to 3 by 8. The body of 3.3 is 1. So Q11 will be 5 by 8. And there are two other points, 2 and 4, which will have probability 0. So my Q1 here is 5 by 8, 3 by 5 by 8, 0, 3 by 8, 0. Now the next thing is very crucial. That is, I have split everything. Now I have actually successfully eliminated one point from that distribution. So the resultant, if I remove this Q1, then the distribution is a 3-point distribution. Correct? So if it is a 3-point distribution, I need to associate a proper probability mass function so that I will be able to distribute it in terms of 2-point distribution. Okay. Let me repeat once again. If I have a 3-point distribution, I need two non-zero probability vectors namely Q2 and Q3, so that at most two of them will have non-zero probabilities. So I want this splitting to happen. That is why what I will do is, let us say P is this vector. I have successfully conducted this experiment and I have evaluated what is Q1. So I will consider P minus 1 by 3 times Q1. This will generate a 3-point distribution. As you can see here, it has non-zero probabilities on 1, 2 and 4. Now I want to split this 3-point distribution into two non-zero probability vectors which have at most two non-zero probabilities. In order to do that, what I have done here is I have multiplied this factor P1 by 2 by 3. That means this P1 will become an authentic distribution on 3 points. And I can use that 3-point distribution formula and I will divide by half Q2 plus Q3. And then when I combine it with this, it will become 1 by 3 Q2 plus 1 by 3 Q3. And therefore I will get P as 1 by 3 Q1 plus 1 by 3 Q2 plus 1 by 3 Q3. This is a crucial step. Please understand. If not, rewind and once again listen to what I have said. So once you do this, then the job is very simple. You are actually computing a 3-point distribution, which we have done in the last case. So my P1, so multiply by 3 by 2 into this vector, you will get P1, which is a 3-point distribution. This 3-point distribution you have to split into 2 parts. So go ahead, choose something that is less than half. Choose something that is less than half. You have chosen that. Then that less than half, j is equal to 1 is my choice. Corresponding to j is equal to 1, I will choose I is equal to 2 because these two are greater than half. 11 by 32 plus 6 by 12. 11 by 32 plus 12 by 32. That is greater than half. So my j is equal to 1, I is equal to 2. So 11 by 30. So again we will use the same. I want the entire probability mass to be at 0.1. So I will put 11 by 32, which is P11, which is equal to half Q21, and therefore you will get what is the value of Q21, which will be 11 by 16. 1 minus of that will give me Q22. Then again you will go to the next iteration. That is, you will come from this, you will compute what is Q2, what should be Q23. Q23 computed here, and then you can again go ahead and compute 1 minus of this is Q43. Therefore, my desired distribution over here will be P is equal to 1 by 3 Q1 plus Q2 plus Q3, where Q1, we have already figured out what is Q1, that was here 5 by 8 0, 3 by 8 0. Q2, we have figured it out here, that is 11 by 16 and 5 by 16 0 0, and Q3 is 0, 7 by 16 0, 9 by 16. This is my two-point distributions of 3 2-point distributions which give equally weighted average of P. This is the 4-point distribution. So what we have done can be generalized for n-step process, that is n-point distribution. So for n-point distribution, what we will do, we will consider a random vector. You know this. Choose j and I satisfying the conditions of lemma define q1. We have done this with qj1 equal to n minus 1 pj and qi1 equal to 1 minus n minus 1 pj. This is what we have been doing so far. Now, this is the crucial step. You assign P1, which is n minus multiplied by n minus 2 by n minus 1 as P minus 1 upon n minus 1 Q1. Okay. After doing this, you continue the same step. So now you will get, because we have started with n point distribution, you will get n minus 1 point distribution. In that case, your scaling factor will be n minus 2. That scaling factor appears here. So continue this process until you get everything in terms of 2 points. Repeat the process to get the desired result, that is P is equal to 1 upon n minus 1 summation over k equal to 1 to n minus 1 qk. This is the desired result that you want. All these steps are done theoretically. So I have this method. Now the algorithm is fairly simple. There is no brainers in this. First, what I want to know is which probability. So now you have an endpoint distribution. You have n minus 1 probability distributions which are equally weighted. Right? So in order, basically you have a probability distribution over n minus 1 points which is uniform. So what you will do, if you have a discrete uniform distribution, you just use the greatest integer function and evaluate it. We have done it several times. So that is what you have done. Generate u1, set n is equal to 1 plus greatest integer function of n minus 1 u1. Again, for sake of completeness, I will repeat. N minus 1 u1 will have uniform between 0 to n minus 1. In the interval 0 to n minus 1, this will be a uniform distribution. Once I take greatest integer function, it will give me a probability distribution on points 0, 1, 2 and so on up to n minus 2. I want a probability distribution on 1 to n minus 1. So I will add 1 to it. So my n is equal to 1 plus n minus 1 times u1. So this is a simulation of a discrete uniform probability distribution. Now, whatever the value of n, what will be the value of n? N will belong to 1, 2 and so on up to n minus 1. We have qk's, that is where k runs from 1, 2 and so on up to n minus 1. So depending on this value of n, you choose your qn. That is the probability vector you will choose. Okay. Now in that probability vector, you have only 2 points with appropriate probabilities. Now you choose a point. Let us say in the previous example, there was a point with probability 7 by 8 and 1 by 8. So you generate another uniform random variable, check if the probability is less than 7 by 8. If so, choose that point. If not, choose the other point. This should be the algorithm. So that can be written in this manner. So you generate another uniform random variable or uniform random number. Set x is equal to jn if the u2 is less than the probability corresponding to point jn. Otherwise, you set x is equal to in. That's all. This is the algorithm. So you imagine how efficient this algorithm is. You don't have to go for evaluation of n points and like you have done in inverse transform technique, whether this number lies in this range or that range. All those things are evaded. Just simply you have to choose the appropriate probability vector, and in those 2 points you decide which point you want to assign to x. This is the beauty of this particular algorithm. It is very fast, very efficient. Okay. Now there are some remarks concerning this algorithm. So now this is a remark about name. I have already used the name alias. So let us try to understand. Now you have qk's. these qk's right now we have not arranged like qkk is less than 1 by n minus 1, that is pk less than 1 by n minus 1 should go in qkk. That we have not done, but we can always rearrange. We can always rearrange such that in each of the particular blocks of probability vectors qkk is greater than 0. Okay. If you do that, it's essentially a permutation of those numbers, permutation of those probability vectors, which you can easily do. If you do that, you don't have to decide what is jn. Jn is k. That's all. Then you will either choose k or you will choose j. The other value, the alias of that buddy, the buddy of k, you will choose. So therefore, the name is alias method. Okay. Another technical remark, how you can improve. Observe that you are actually generating two uniform random variables. So if when you are generating the first uniform random variable, that is u1, you can also consider n minus 1 u1 minus n minus 1. As I have already mentioned, this number is uniform in 0 to n minus 1. Capital N is uniform on 1 to n minus 1. This number will be uniform on 0 to n minus 1. When you are multiplying this with n, if you divide this number by n minus 1 and take this n minus 1 common, this particular thing is actually uniform over 0, 1. Done. That means this iteration, we are not, again, we are not using the value for the next iteration. So the iteration can be independent. And therefore, rather than computing u2 in step 2, we can simply use n minus 1 u1 upon the greatest integer function of n minus 1 u1. This is the greatest integer function of n minus 1 u1. And save on the cost of generating the second uniform random variable. That's all for today. We have finished special techniques for discrete random variables.